Fluid flow. Okay. And so basically here, I'll just get rid of all of this. I know you saw it there, but it wasn't my intention. All right, fluid flow. So we basically have an ideal fluid right here. And an ideal fluid is a fluid that is incompressible. Okay, that means that its density is constant. So basically, if you don't change the density of the fluid, it's incompressible. And it has no internal friction or viscosity. Viscosity has been a term that's been somewhat elusive to me, but I like to think of viscosity in terms of, how a thing flows or the forces that are inside of the fluid and how those forces interact with one another, as well as how those forces interact with the surface that it's in contact with. So you have honey, you have water, you have oil, you have all kinds of different things, and they have different kinds of viscosities associated with them. And again, it has to do with these forces that are acting on the inside of that fluid. Okay, and it's going to affect how it flows. Cool. So that's great. There are more ideas behind this, but this is pretty this is this is letting you know that we're dealing with an ideal fluid because all fluids have internal friction. It's saying that it doesn't have any. It's saying that this fluid is inviscid, and the only fluid that I know of that's inviscid is called a superfluid, and that's when you get very close to absolute zero. Okay, so let's continue right on with fluid flow, and we have this idea, and it's called the continuity equation. Okay, and we'll most likely we'll talk about it right now, and it looks like this: delta V over delta T equals to A1 times V1 equaling to A2 times V2. So this is called the continuity equation, and it's coming from the conservation of mass. Okay, and let me just read the definition to you real quick. It says continuity equation. This equation expresses conservation of mass for an incompressible fluid flowing in a tube or some other channel. It says that the amount, either the mass or the volume, of a fluid flowing through a cross section of the tube in a given time interval must be the same for all cross sections. Okay, that is what this equation is saying right here. Interesting, because the cross-sectional area can change, which means that if the cross-sectional area changes, then we're going to have something that's a little bit different. And when I say a little bit different, you're going to have a different velocity. So right now, let's just say that we have a certain cross-sectional area, A1, and it's moving at a velocity V1. And let's say that the area reduces in size. That means in order for this equation to remain balanced, the velocity has to increase in size. So this is the idea behind the continuity equation and the conservation of mass. Okay, in the next video, we're going to go into deriving this continuity equation, and it's going to lead to Bernoulli's equation eventually.